All right, guys, sorry to be away yet again, but that's how she goes, I guess. So today we're going to do a lesson on three-dimensional problems. This will be the last topic in this unit, but we'll get some practice with it, don't worry. So here we are, looking at that. And we're just going to do two examples together, and then I'm going to set you on some homework, and then we'll take a look at tomorrow. And I'll just quickly remind us that, we're going to need all the tricks we've got here, but we can remember that, we've got side A over sine A equals B over sine B equals C over sine C. We've got sine law if we need it, right? And we've got cos law, right? If we need it, we can say that A squared is equal to B squared plus C squared minus 2BC times the cosine of the angle opposite to A, right? So we've got these if we need them. We're going to need them. And obviously, we know our primary trig ratios as well, right? So these will be the tools of the trade we use today, and let's get to it. So, Scarlett and Aidan decide to walk to determine which of the two routes is faster in a shopping mall. They both agree to walk at a pace of 1 meters per second as they travel the two routes. Scarlett walks from the starting point to the elevator, and then takes the elevator up to the end point, just outside the doors of the elevator. And the elevator travels at a speed of 0.4 meters per second. Aidan walks along a path that is 20 degrees to the path taken by Scarlett to a set of stairs that lead up to the end point. All right, so it's going to go there and then there. So if you watch the path, Scarlett is going to go here and then up, and Aidan is going to go here and then there. And at the speed, this is going to be 1 meters per second all the time because Aidan is always walking. And Scarlett is going to go 1 meters per second while walking, but then she's going to go only 0.4 meters per second while going up the elevator. So just so you know, that pink color here, that's going to be the speed. So all we need to know then to know who's faster is, if we want to know time, it'll just be for each of these legs, the distance they go times the speed. So we know the speeds. What we need to figure out is the distance. And unfortunately, we're only given one distance to start. We know this distance, that trip up the elevator is 5 meters, but nothing else is given. Now, the thing I want to note is that this is three-dimensional. The idea is that this here is the ground, right? But this is a staircase, right? Like this is going up the stairs. So that's important because these triangles are on different planes from each other. They're on different planes from each other. And that means the only thing they have in common is the side they share. The only thing they have in common is the side they share. In other words, this whole angle here, normally we would think of as adding to 360 if they were all lying flat. But they're not lying flat, and you'll see they don't add to 360. 90 plus 90 is 180, and another 80 is 260, because again, you have to imagine that these ones are going up and down, and this one is on the XY plane. It's going left and right. Just a totally different thing. So they're not connected to each other. But they do share sides in common. This triangle here shares this side that we've highlighted in yellow with the bottom triangle. So we can use that to solve the information we need. So what I'm going to do is I want to figure out the lengths of all the missing triangles. And the way we do that, let's start with triangle 1 first. And triangle 1 is a 90-degree triangle. If we look at it all by itself, it looks just like that. And the only thing we know about it is that this is 5 meters, and that's 90. So is that enough information for us to solve anything? And the answer is no, it's not. So we can't solve that. At least not yet. So we'll come back to it if we need to. With that in mind, let's look at triangle 2. This one is a little bit more promising. Triangle 2 is a 90-degree triangle as well. We know that this is 17 degrees. We know that that's the right angle. And we know that that's 5 meters. And that is enough information for us to solve. So let's solve for this here. And if we know that this is our theta, then we can label sides. And we would label this side as the opposite. We'd label down here as the adjacent. And we'd label here as the hypotenuse. And now, pause a minute, pause this video, see if you can solve for the triangle. And we'll come back. Okay, hopefully we're back. I'm going to solve for the hypotenuse first, not that matters. I'm going to say the sine of 17 degrees is equal to the hypotenuse over the opposite, which I know to be 5 meters, right? And so then, just very trivially, if I multiply this side by 5, and I multiply that side by 5, the 5's will cancel, and I should get that the hypotenuse is equal to the sine of 17 times 5, and that should give me a hypotenuse that's equal to, I can't do that in my head because I don't have sine tables memorized, but we'll say the sine of 17 times 5 should give us 1.46 meters. Oh, wow, okay, you guys are probably all yelling at me right now, as you should be. Why did I put hypotenuse on top? I don't know why I put hypotenuse on top. Probably because I'm silly. I'm a silly boy. What we would say is that the hypotenuse goes on the bottom. So this would be 5 meters divided by the hypotenuse. And now, the easiest thing to do is just to cross multiply. And if I want to solve for the hypotenuse, it will be these two things multiplied by each other. So 5 times 1 divided by the remaining thing, sine 17. Sorry about that. This lesson's confusing enough to begin with, and here I am making it tricky. Sorry about that. 5.1 divided by the sine of 17 is going to give us a much better number that makes sense, 17.4. I like that number. So, we can add that here. We can say that that is 17.4. And we can solve for the adjacent while we're at it. And we can say that the cosine of 17 degrees, cosine is adjacent over hypotenuse, would be the adjacent divided by 17.4. Put that over 1, we can just cross multiply. We do these two things multiplied by each other, divide by that. And so we should get the adjacent as being equal to 17.4 times the cosine of 17 degrees. And we can get our calculator. And we get 16.6. And if we want to, we could go put these back onto the original. We could say that this staircase is 17.4 meters, right? And that this length down here is 16.6 meters. And that's going to be helpful because now that we've done triangle 1 and we've done triangle 2, now let's take a look at triangle 3. And triangle 3 looks like something like this. We're seeing it from a perspective. We're seeing it from an angle. If we were to draw it flat, we know it's going to look kind of something like that, because we know this angle here is 20, right? That's 20 degrees. That's 80. And what's this third angle? Well, that'd be 180 minus 20 minus 80. And that's going to be 180 minus 80 is 100, minus 20 is 80 again. So that's also going to be 80 degrees. Okay? And we now have a number in here. See, we didn't, but if you look here, when we solved for this side, that's 16.6, that is shared between these two triangles. You can't share angles between two triangles if they're in different planes, but the lengths can still be shared. So that side over here is 16.6 meters. And now we should be able to say that 16.6 over the sine of 20 is equal to question mark over the sine of 80, which is actually equal to question mark over the sine of 80 again. So we're going to have the same math to do twice, which is fine. So take a minute and solve that if you can, and we'll come back together. All right, hopefully you took a moment while we paused that to solve for it. This should be just that the question mark is equal to, we're going to cross multiply, right? So we'll multiply those two things together and divide by that. So we would say 16.6 times the sine of 80 divided by the sine of 20 should give us how big those two sides are. And again, maybe you can do signs like that in your head. I certainly can't. 16.6 times the sine of 80 divided by the sine of 20. And we get 47.8. So I'm just making that smaller. So 47.8 meters. And because that fills in both these question marks, because they're both 80 degrees, we can just fill that in. That's 47.8 meters, and that's 47.8 meters, which we can then go to our original diagram and put in. So even though it doesn't look like it here, by virtue of this being, and this is what you got to watch out for when you're looking at things in three dimensionals, this doesn't look like it, but that's also 80 degrees. It doesn't look like it just because the angle we're looking at this whole thing at, right? But we know that triangle sides have to add up to 180. And that being 80 means that this is, what was the number again? 47.8? Yeah. That means that this is 47.8 meters, but this is also 47.8 meters. Okay, so let's now talk about Scarlett's walk. Scarlett's going to walk 47.8 meters at 1 meter every second, right? And what could we say? We could say distance equals speed times time, right? Therefore, time is equal to distance divided by speed, right? So that first walk would be, so she has the A part, which is 47.8 meters divided by 1.0 meters per second. And I can do that math in my head. That's 47.8 seconds, right? But then we have the B part of Scarlett's walk, which is going up the elevator, right? And going up the elevator is 5.0 meters at 0.4 meters per second, right? And if we do that math, I don't actually trust myself to do that right now. 12.5 seconds. And we put that together for a total of, that's going to be a 3. 2 is 9, plus 1 is 0. So that's going to be a total of 60.3 seconds for Scarlett. All right, let's contrast that with our friend Aiden. Aiden has, in the end, the exact same A part, right? So Aiden, A part is the exact same. In the A part we go 47.8 meters at a pace of 1.0 meters per second. That's going to give us 47.8 seconds. And then Aiden's B part, still walking, keep in mind, 17.4 meters at a pace of 1.0 meters per second. And that's going to give us 17.4 seconds. And we put those together for a total, we should get 2, 7, 7 is 14, this one is 15, 4 and 1 is 5. There you go. 65.2 seconds. All right. So therefore, Scarlett's route is faster. And then B, how much faster? Well, that's trivial. You could just do Aiden at 65.2 minus Scarlett at 60.3 seconds. And the distance, that's going to be a 9. That's going to be a 4. That's going to be a 0. So it's 4.9 seconds faster. Okay, now, there's a lot going on there. Do we see that there's a lot going on there? It's a tricky question, to be sure. But that's okay. We got it. All right. Now, let's try to solve a three-dimensional problem here. All right? Now, again, we're going to make a rule for ourselves, which is, remember, triangles in different planes, i.e., not sitting on the same flat surface as each other, can share sides but not angles. So the side lengths on one plane, if you look here, we're able to share all of these side lengths, but the angle in one triangle has nothing to do with the angles in another triangle if they don't sit on the same plane. You can't draw any conclusions about them. All right, let's try another one. A surveyor is on one side of a river. On the other side is a cliff of unknown height that she wants to measure. And the surveyor lays out a baseline AB of length 150 meters. From point A, she selects point C at the base of the cliff and measures CAB to be 51. She selects point D on top of the cliff directly above C and measures an angle of 32. She moves to point B and measures CBA as 62. Find the height of the cliff. All right. This question would be brutal if we didn't have a picture, if we had to just describe that, but we get a picture. So the idea is that we've got this cliff back here, this gray wall. All right, there we are. And down here we have the river, so she can't just cross it. All right. And so what she does is she stands here, she puts a flag up. Oh, look at that, there's a flag. And then goes and stands here and puts a flag up. Oh, look, it's a flag. Why is it blowing the other way? I don't know, couldn't tell you. And then goes back here and measures, picks a spot at the cliff and a spot right above that, and then takes a bunch of measurements. All right? And the question we want to know is how high is the cliff? This is what we want. Okay, well, this one's not so bad. Just to walk through what it could look like is that in the end, this triangle, this triangle here, triangle 1, is the one we really care about, right? So triangle 1, we have a right angle triangle. It looks like that, right? And we know this to be 32 degrees. And what we want to know is this, right? The problem is we have no lengths. There's no lengths in this triangle to work with. So what we need to do is get a length on there. And the only length we're going to be able to get on there is the side they share. They share this highlighted side. So we're going to have to use the second triangle to try to figure that out. And so what we would do if we have the second triangle there, it looks like this. 51 degrees, 62 degrees, and let's go. And then the other thing we know is that this down here is 150 meters, right? So let's get to it. What is this missing angle here? Well, the missing angle is trivial to find. We would do 180 minus 62 minus 51, right? And probably you can do that in your head. That's what? 60 and 50 is 110. That's 113. 180 minus 113 is 67 degrees. So that should be 67 degrees there. All right. And the side we care about right now, the side that's going to be useful to us right now is, that's angle A, that's angle B, and that's angle C. We like that side B because keep in mind that side B is the shared side with the triangle we actually care about. So we do a lot of questions like this. So we'd set up the sine law and we would say B over sine 62 is equal to, and then which side do we want to use? Well, not A, we don't know that. So what we're going to use is angle C beside C, right? Because we can then say 150 meters pairs up with a sine of 67 degrees. And now we can cross multiply. We can say B equals, these two things multiplied to each other, divided by that, right? So 150 times the sine of 62 divided by the sine of 67. And we would get B equals whatever this equals. 143.9. And so now we can go put that in here. We can say, well, that's 143.9 meters. But of course that goes into the triangle that we actually care about. We now know that to be 143.9 meters. And now, if we call that theta, we can just use SOHCAHTOA here. We can say that if that is theta, then we would call this, let's not use h for height. Let's use this as the opposite. We'd call this the adjacent, and we'd call this the hypotenuse. And we could say that the cosine, oh, the opposite's what we care about, right? We want this side. So we want the opposite. We know the adjacent. So we could say the tangent of theta is equal to the opposite, which is what we're looking for, over the adjacent, which is what we know. Then we could say the tangent of 32 degrees is equal to the opposite, which we don't know, divided by 143.9 meters. And if you want to set this up as cross multiplying, you can do so. We could say we would multiply those two and divide by 1. Or if you just want to solve it algebraically, you can say that to get opposite by itself, you'd multiply this by 143.9, and you have to do the same to both sides, whichever way you like. And we would get that the opposite then is equal to 143.9 times the tangent of 32 degrees. And this would give us an opposite of, let's see, 89.9 meters. And so now if we go back here, what we found is the height of the cliff to be 89.9 meters. So questions like this really can range from quite tricky. We let off with a really annoying, tricky one here, to a little bit more straightforward, but the challenge to them is you have to kind of think in 3 dimensions. You have to remember, and tomorrow we'll actually work at modeling a few of these in 3 dimensions. You have to remember that if you look at a triangle 3-dimensionally like this, you can see some strange things, right? We can make the angles kind of look different than you would expect them to look. And so then, if we had, you know, right, you can start to see how these can get quite tricky, right? Anyway, we'll do some messing around with that tomorrow. I hope that's helpful. There's some homework on the bottom here. Good luck. I'll see you.